So one thing we're interested in calculus is this idea of continuity and bounds. Okay, so bounds just represent what variables are part of our domain and range. Okay, so in this case here, our bounds would be, we start at 0. Okay, it looks like we have this point is a hole, so it's what we call discontinuous there. But it is still, we still have that part of our domain. Okay, so that value of x equals 1 still represents part of our domain. We have, again, it seems like it's discontinuous here, but then that still is defined at that value of x equals 2. So we have all the x values all the way up to 2 so far. And then, in fact, we have all the x values all the way up to 3. So the bounds of this case, of this function, are going to be, the domain of this function, I'll just list it as domain, is going to be from 0, including 0, all the way to 3. Okay, including 3. And this is what we call a closed interval. Now, continuity is something slightly different. Okay, so we have, in this case here, continuity, although we have all the x variables from 0 to 3, okay, and it looks like we also have all the y variables. In fact, we can write a range here because that value of 2 is defined. So we have all these y variables from 0 all the way to and including 2, and then from 2 all the way to 3. Okay, so our range is going to be from 0 to 3. Okay, and this again is a closed interval. Now, this is discontinuous, so we have to then kind of think of what's happening here. So this issue of continuity is important. So at this point here, at x equals 1, if I were to draw this, I have to lift my pen up and then draw there. So anytime I have to lift my pen up to draw the function, we have a discontinuity. Okay, so this is discontinuous. At x equals 1. Okay, and this is what we call a removable discontinuity. Okay, so it's a hole in the graph. And then we also have a discontinuity here, okay, because it breaks apart. And again, our eyes don't lie when it comes to continuity. Now we're going to define continuity fairly formally, but it's still our best measure of continuity is just our eyes. Does it break apart or does it not break apart? So here at x equals 2, it is also discontinuous, okay, because it breaks apart. This is what we call a jump discontinuity. Okay, and you don't really need to know the names of these, but they do actually have some names to them. So although our domain and range is continuous from 0 to 3, okay, there is this discontinuity happening at these points. Okay, so at the point x equals 1, there's a discontinuity. At x equals 2, there's a discontinuity. Okay, let's move on to inverse here. Inverse functions are basically switching x and y values. Inverse can be thought of a few ways. It can be the switching of x and y values. We can switch x and y variables to get an inverse. So in this case here, we just switch the x and y to get the inverse of this function over here. Inverse is also the inverse operation. Okay, so for example, add and subtract are inverses of each other, times and divide. In this case, squares and square roots. So when we do the inverse here, the square root function is going to be the inverse of the squared function. Okay, although they're not quite the perfect inverse, and we'll see visually why they're not quite the perfect inverses of each other. Okay, so there's a little bit of a problem when we do that, and we kind of saw this algebraically, and you may have wondered why, but we'll show visually why these are not perfect inverses of each other. Okay, so if I'm going to draw this, I'm going to draw this at x's, I'll draw my points in here, at x is 3, y is 0, x is 4, y is 1, and let's use one more point, x is 7, y is 2. Okay, so this is my original function. Okay, the inverse is basically just going to switch all these x's become y's, so it becomes 3, 4, 7. Okay, and all the y's become x's. So this becomes 0, 1, 2. Okay, and switching the x and y coordinates, switching x and y variables really are the same thing. And when I graph this new function, this is what my inverse is going to look like. It's going to be 0, 3, 1, 4, and 2, 7. So there's my inverse function. Okay, so inverse has this relationship where we switch x and y variables, x and y coordinates. Now, if I draw the inverse over here, it has a physical property as well, in that the inverse, if I draw that inverse function, it is a reflection of the red function there. It's a reflection across this diagonal line, y equals x. Okay, because when I switch to y and x and a y equals x function, it just stays the same. So that's our invariant point or our mirror point. Now, if I undo this, and notice that this shape is half a parabola. Okay, it looks like half a parabola. I'm just missing this half over here. Okay, so why don't I have the full parabola? Well, these are not perfect inverses of each other. So when I solve this equation, so if I solve for y, I get x squared equals y minus 3. So I get y equals x squared plus 3. Now, if I were to draw this, I would draw the whole parabola. But the problem is, when the square root is only defined for the positive, whereas parabola is defined for the negative and positive. And we saw this the other way. When we solved the square root, when we solved the squared function, we had to do plus minus because we had to get both the top part of the square root and the bottom part of the square root to get the mirror image or the inverse. Okay, so these are not perfect inverses of each other. So it's important when we're doing inverse that we also not only switch x and y coordinates, x and y variables, okay, we also have to switch domain and range. So here the domain of this function was from 0 to infinity. Okay, so that means then that the range of this function is going to be from, so the domain was from 3 to infinity, okay, from x is 3. So that means that the range of this function is from 3 to infinity. Okay, so the domain is from 3 to infinity. My range of this function was, the red function was from 0 to infinity. Okay, it's going to go from 0 up. So the range of this, the domain of this function has to be from 0 to infinity. Okay, and that's why we don't include this half, because the domain, it wasn't actually part of the range of the original function. So it can't be part of the domain of the new function, of this inverse function. Okay, so that's very important to that we remember that we can't change, we can't introduce new parts of this into my inverse function. These are perfect inverses of each other only if we change the range here to the domain here. And that way we're not going to use this whole parabola. We're just going to use half the parabola with this domain of 0 to infinity. Okay, so that's a very important concept. That's something that we can't forget when we're doing inverses. Otherwise, we may state that this is the inverse. Well, technically it's not quite the inverse, okay, because there's not a match. The parabola doesn't actually match that red square root function if we were to say that there's the inverse. Okay, and same with the other way around. The square root is not the inverse of perfect inverse of a parabola. Okay, so if I had a parabola and I undid it with a square root, I would only get half the square root. And that's why we need plus minus, right? That's why we need the plus minus square root. So if I just did this, I just end up with square root. Okay, but in order to do the inverse, I really need the positive and negative because that's now an inverse. So that's why the plus minus shows up when I solve by square rooting.